Okay, recording is on, and so let's get started. So first off, any questions before we dive into the stuff? Did you guys all hear the announcement that we're going to be doing this for the rest of the school year? You will not be going back to the school building. I don't know how we're going to handle textbooks because you guys obviously need to return those. Uh, are you saying that sarcastically? I'm not too sure. Teaching from home has its advantages, but it also has its disadvantages too. Oh, about your graduation. Yeah, well, Mr. Wilson should have sent an email. Uh, we're planning to have something. We just don't know when it's going to be. Um, so, yeah. Okay, so if there's no questions, let's go ahead and dive into the fun stuff. Okay, so I hope you guys agree that the quiz questions were really, really easy. Okay, so the fourth right-hand rule is the same thing as the third right-hand rule. I have no idea why the author wants to call it the fourth right-hand rule. It's the exact same, so definitely nothing to worry about. Okay, the difference between an electric generator and electric motor inside, not really any difference at all. Now, as I mentioned last time, there are a couple little tweaks that they can do to make a generator work a little bit more efficiently for generating and to make a motor work a little bit more efficiently for being a motor. So when I say that there's no difference at all, that's not completely true, but fundamentally there's not. And in fact, one thing that I love to do, and were we back in my classroom, I would do it, is I take a motor and I attach a handle to it and I crank it and I attach a light bulb to the other side, and you'll see that a motor does in fact work as a generator. Okay, it really does work that way. Okay, next question. All right, so basically just what's the right equation to use for the homework? So I trust you guys all got that one right. If you didn't get the right equation, you won't have done the homework right. Okay, so again, just a quick thing to make sure you understand the basics for before you do the homework. So yeah, if you just look at how many turns there are on the primary side, how many turns there are on the secondary side, and that's your multiplication factor. So you're either going to step up by that much or step down by that much. So in this case, this was a step down transformer. All right. And the secret word was Zamboni. So I hope you guys are thinking about a really good secret word for today. It needs to be classy, or well, maybe not classy, but it needs to be unique. It needs to be unique. Okay. Uh, Okwo. Okay, and I don't know what Okwo is. That a different language? But hold off on the secret word for now. Okay, let's talk about last night's homework. All right, here are the answers to the problems that you weren't able to just look in the back of the book. You can see that there's two of them that I want to make sure we discuss, 14 and 16. So if you have a question on those, hold off. But number 2, 4, 16, do you have questions on any of those? Did I mess up and put the wrong answer down like I've been known to do? Can we go over number 4? You
I have a
bet you.
question.
Okay.
Um, on numbers, I think 1 and 3,
Uh-huh.
they ask for an answer to the equation that we have, which is fairly simple. But then they ask something about a current with an omega, and I had no idea what that was.
Oh, uh-oh. Yeah, okay. That's part of what we skipped over. And oh, I should have read more carefully. Let's see. Okay, this is 20. Oh, this is 25. I'm in the wrong chapter.
We
The
never got V equals IR.
Yeah, the omega is just talking about the number of number of ohms, and oh, if I forgot about that, then that's my bad. Hang on a sec, I almost got it. Okay. Oh, yeah, part B. The wire is part of a current with a total resistance of 6 ohms. What's the current in the circuit? Yeah, you are right. I did not anticipate that. I should have read this more carefully. Yeah, in order to answer part B, you need to know something called Ohm's law, which is in the chapters that we skipped over. So don't worry about part B. I'm not going to put a question on the test like part B. And was there another one that was the same way? Okay, yeah, number 3B, the same thing. Okay, so don't worry about any of those. All right, so Hiram is asking about number 4. He says it's still confusing. Okay, so number 4 says we got a horseshoe magnet mounted so the magnetic field lines are vertical. Okay, so you need to understand magnetic field lines come out of the North Pole and they go in to the South Pole. Okay, so that means this magnet we've got, the bottom part of it is the north part of it, the up end is the south. Okay, so a student passes a straight wire between the poles. All right, so here's the magnetic field lines. Here's a wire, and I'm going to push this wire through those magnetic field lines. Okay, so the charges inside the wire, the electrons and the positive charges, they're going to feel a force. So let's see what direction they're going to be. Okay, so we're going to use the right-hand rule. So let me use my left hand as being, so these are the magnetic field lines. Okay, here's the wire. So I'm going to push the wire away from me. So the right-hand rule says I take my thumb, and my thumb tells me the direction that the charges are being, they're moving. Okay, and then my fingers need to be aligned with the direction that the magnetic field lines are, which is up. Okay, so then my palm tells me what direction the force on the positive charges are going to be. Okay, so the forces on the positive charges are going to be like this. Okay, so that's the way we approach that one. So Hiram, does that answer your question? And while you're thinking about that, so Ellie wants to go over number 16. Okay, so 16 says we have a step-down transformer. Okay, so that means we got more turns on the primary side than we do on the output side. Okay, so we got 7,500 turns on the primary and 125 on the secondary. So I'm going to take 7,500 divided by, what was it, 125? Okay, so that means that the multiplication factor, or in this case, the division factor, is going to be 60. Okay, so the difference between the voltage on the one side and the other side is the difference is a factor of 60. Now this is a step down transformer, so that means that the output voltage is going to be 1/60th of whatever the input voltage was. So if the primary voltage was 7.2 kilovolts, so that's 7,200 volts. So 7,200, divide that by 60, and I get 120 volts. Okay, so that answer your question there, Ellie? And does anybody else have any questions? So I'm not seeing a yay or nay, so I'm going to assume that no news is good news. Okay, good. All right, now I'm seeing a yay. All right, so let's talk about number 14 and number 16. Okay, so number 14. 14 is saying, explain the fundamental operating principle of an electric generator. All right, so I think that we went over this pretty thoroughly. I want to hear one of you do it, okay? And I will even help you. I will give you, here's a motor, here's a generator, okay? So I'd like one of you to volunteer, turn on your mic and explain, you can use these pictures if you want, explain the fundamentally, how does a generator work? How does a motor, actually, let's see what they say. They're saying generator. Okay. So how does a generator work? Who wants to step up and do that? You want me to pick one of you at random? I can do that. Let's see who's online here. Oh boy, we got a lot of people online. Let me just pick somebody at random here. So Cohen, would you be willing to turn on your microphone and explain to us how does a generator work? Come on, Cohen, I see you're online. Oh, okay. I'm not hearing you, Cohen. You got to unmute yourself. Here, I can unmute you for you if you want. Okay, Cohen, you have now been unmuted. Go ahead and talk.
Okay. Can everyone hear me properly?
Yes.
Okay, great. So basically, in a motor, current moving through a wire causes the kind of orangish coil to be affected by the magnetic field. And basically, a motor is just the reverse effect, where if there's no current flowing and you affect the wire by rotating it manually, the magnetic field will kind of, by like inversely cause current to move through the wire.
Okay, you said motor, you meant generator.
Yes.
Okay.
Sorry.
Yeah. Okay, so here's the motor. So the current flowing through here, as the charges move, they feel a force on them, and that force is going to push them upward and was going to make the thing twist. But with a motor, or I'm sorry, with it, I did the same thing you did there, Cohen. So with a generator here, the current is not, well, there's no battery pushing it. So if we don't crank the thing, the current's not going to flow. But we are cranking the thing. Okay, we grab onto this handle here, which I realize doesn't look very much like a handle, but use your imagination. Okay, pretend that's a handle. Okay, so when we force that thing to turn, then we're taking these positive charges and we're forcing them to move vertically through this magnetic field. They're going to experience a force on them. The force is going to make them want to flow. So we've created voltage here. Okay, so you guys need to be able to explain that, because you never know. It might be a question on next week's test. Wink, wink, nudge, nudge. We'll talk more about next week's test in just a minute. Okay. And the generator, depending on how you do it, you could have a DC generator, so where you have one ring with the split in it. Okay, so the split ring commutator. Or if you want, you can use two rings here, and you get an alternating current generator. And it turns out that alternating current generators are the most common kind, but direct current generators, they do sell them, and there is an application for them. Okay, and then the other one was, let's see, I got too many windows. Okay, number 20 was the other one here. Let's see, what was that one asking? Okay, transformers and current. So explain why a transformer may only be operated on alternating current. Okay, so let me pick somebody else here. Dean. Okay, can you turn on your mic and tell us why is it that a transformer only works if the voltage that you're feeding into it is alternating voltage?
Yeah, okay, so AC, the magnetic field is constantly changing, which is what induces the current in the output coils. And because DC's magnetic field is static, it doesn't have a changing magnetic field to induce current.
Okay, everybody understand what he said there? Okay, as long as I keep flipping this battery, so the battery that you see on the screen there, you see I'm oops, sorry. Okay, let me go back, okay, there. All right, so as long as I keep flipping that battery upside down, right side up, upside down, right side up, as long as I keep doing that, the magnetic field lines will be changing, okay? And as long as they're changing, then over on the right side here, again, too many windows. I've got a bunch of windows that I need to keep up when to run this meeting here. Okay, so as long as I keep flipping it back and forth, over here on the right side, the changing magnetic field will induce an electric field, but a static field does not. Okay, so let's suppose that I flip the battery up and I leave it up. Okay, so over on the right side, current is flowing through this coil, which means that there is a magnetic field inside that coil. but a magnetic field is a constant field. It doesn't change. And if that if it doesn't change, then the electricity, the charges over here on this side, they don't feel any force acting on them. Because you remember what we said several class periods ago. If I've got a magnet and here's a charged particle, if that charged particle is moving, or if the charged particle is stationary but the magnet's moving, as long as there's some relative motion between the two of them, then it will feel the force. But if that charged particle is not moving, it will not feel the force. And so it's the change in the magnetic field. If that charged particle does not feel the magnetic field changing, then it doesn't feel any force on it, so it does not going to work as a transformer. So you guys all need to understand that. All right, so new material for today is chapter 26, but let me just pause for a real quick second. Before I go on to the new material, let me ask one last time. Any questions about the old material? So I need some sort of response.
No.
Okay, no questions. Okay, good. All right. So chapter 26, this is the last chapter that we're going to go into before we take the test. Next week, we are going to take a test. Let me just tell you a little briefly here what my plan is. So today we're going to talk about 26, and I'll give you some homework out of the book. On Friday, we will go over the answers to that homework. I will introduce a few new concepts. Basically, I'll just fill in a couple of holes where we kind of skipped over a few things. I do not plan to give you a homework assignment on Friday, but I will give you a quiz. So the quiz questions will be a little bit harder than usual. You know, usually the quiz is basically just a joke. You know, did you stay awake? So if you did, you can pass the quiz. Friday's quiz will be a little bit trickier. There will be some actual serious questions in the quiz, but other than that, there won't be any homework. So it won't take you very long. I don't like to give homework on Fridays with this new arrangement here. I think you guys hehomework twice a week. That's enough, I think. Okay, so then on Monday.
I was wondering.
Yeah, go ahead.
You know, I know that on the quiz things that we normally do, one of the questions is what's a secret word, and the thing is, the secret word's usually at the end. I'm beginning to wonder if maybe we should do it in like the middle or something.
If you'd like to do that, I'm open to that. Okay. When you say the end of the class or the end of the quiz?
Let's see. At the end of the video, you always say what the secret word
So
will be.
you want to do it now in the middle of the video?
Yeah, that way
Okay.
we make sure people actually watch it.
Okay, I like that thinking. Well, Jaron, do you want to be the one who suggests the secret word?
Let me think about it.
Anybody else want to pipe up? Whoever can come up with a good secret word first, I'll take it. But it has to be a unique word. OWO. Okay. All right. I will go with it. I have no idea what an OWO is, but Annie has suggested it a couple times, so I'm going to go with it. Okay. So, Jack, I'll never let go. Okay. That's a good one. I would like that one, except that Annie beat you to the punch here. Okay. So the OWO. Now, tell me, Annie, is that actually a word, or is that just a bunch of letters you threw together at random? Okay, so apparently she just threw a bunch of letters together at random. So that's okay with me. I can accept that. Yeah, teens these days. Yeah, what are you going to do with them? Okay, so the secret word for today is OWO. All right. And I think what I'll do when I make up the quiz is I'll have the other secret words will be equally nonsense, just random combinations of letters. Okay, so thank you for that suggestion, Jaron. Okay, so let's get moving. I gotta put ooh. Okay, I'll do that. That one will not be the right answer, but yeah, I'll throw that one on there. Okay, let's get serious here. Okay, so chapter 26 is the last chapter we're gonna go through, and chapter 26 is where everything comes together, and you'll find out the reason why I do things in the order. I talk about light first before I go into electricity and then magnetism. You're about to find out the reason why I do it in that order. Okay, so first off, let's just do a real quick review because this is going to help us to understand things here. Oops, let me get rid of some of my windows here. Sorry, okay, there we go. All right, okay, so we've got a step-up transformer here. And as we talked about just a minute or two ago, this step-up transform only works if you constantly flip the voltage back and forth. As soon as you stop flipping the voltage, the step-up transformer stops working. Okay, so why? Why does it all work? And then again, hopefully this is all review for you. Okay, so let's say that I take a battery, I connect up a wire without using a resistor, which some of you know is very bad, because what's going to happen is the wire is going to heat up. But let's assume that there's enough resistance there, so the wire isn't going to burn up. Okay, so I've got current flowing through the wire, and the current is flowing downward. Okay, so here's a good review question. What is the magnetic field going to look like? Okay. And let me toss that out to you guys. Somebody want to give me a verbal description? What is the magnetic field going to look like if I have current going downward through a wire? Come on, I need somebody to pipe up here. Nobody wants to step up? Right-hand rule, thank you. Yes, and the book calls this the book calls it the first right-hand rule. So here is my pen, and the pointy part of the pen, that's the direction the current is flowing. So we see the current is flowing downward. Okay, so what I'm going to do is I'm going to grab the pen using my right hand, okay, and I'm going to grab it so that my thumb is pointing the direction that the current is flowing. And remember, this is the traditional current that we're talking about, the positive charges, back before that they knew that there was such a thing as an electron. So I grab it with my right hand, thumb like that. Okay, so my fingers will curl in the direction that the current will look like. And so basically what happens is the current is going to, whoops, okay, the current is going to look like this. Okay, so in front of the wire, the current is going to be going from right to left, and then behind the wire is going to be going from left to right. Over on the left side of the wire here, it's going to be going into the page. Over on the right side, it's going to be coming out of the page. Okay, and so now if I flip the battery up and down, so the current is going up for a while, and then the current's going down for a while. Current's going up for a while, current's going down for a while. Okay, so what we have then is all around the wire, we have a magnetic field that is changing. Okay, and so if there was a positive charge sitting there, so before we have the current flow, here's this positive charge just sitting there, minding its own business, not bothering anybody, and somebody all of a sudden hooks up a battery, and so a magnetic field appears that wasn't there before. So we've got a changing magnetic field. So that charged particle is going to feel a force acting on it. Okay, whenever it's in a region of space where the magnetic field is changing, it's going to feel a force. And now that magnetic field could be changing because the charged particle is moving through the magnetic field area, or it could be that the charged particle is sitting still and the magnetic field is the thing that's moving, or as you see here, it could be that nobody's moving, but the battery is, okay, which wasn't there before. All of a sudden the battery's hooked up, and so this magnetic field appears out of nowhere. So the effect is exactly the same as if they were moving. So this charged particle now feels a force that is going to push it in a certain direction, and the direction that the force is going to be is always perpendicular to the direction of the magnetic field. So if you can see here, the magnetic field is coming out of the page. Okay, so that charged particle is either going to feel a force going up or going down, depending. Okay, and okay, so So it's going to feel a force that's in the vertical direction. Now, fundamental question for you. Why does a charged particle feel a force? What is it that causes it to feel a force? And it's the same question that we talked about before. Fundamentally, what is gravity? Okay, so here's the Earth. Here's some satellite. Maybe it's the moon, maybe it's an artificial satellite. I don't care. It's something that's in the vicinity near the Earth. That object over here is going to feel a force pulling it towards the Earth. And so this is a question that I've asked before, but it's worth asking again. How do you explain that? How is it that the Earth is able to reach out with invisible fingers and grab this object and pull this object towards it if there's supposedly nothing in between them, right? You should be able to take your hand, pass your hand in between here. There's no strings, there's nothing, and yet somehow the Earth is able to grab the moon and pull it towards it. Well, the answer to that question, which we talked about before, and I hope you guys really appreciate the significance of this, Lefebvre. Very good, Josh. Yes. Okay. Because empty space is not empty. That's probably my all-time favorite phrase. I like that even more than the phrase, from this point on, it's no longer a physics problem. Now it's just a math problem and you're good at math, right? Yeah. So I have a bunch of catchphrases. You know, maybe we'll make that be a quiz question someday. What are Mr. Hendrix's favorite catchphrases? Okay, so anyway, there really is something there. Even if space was a total vacuum, even if there was absolutely no molecules at all, okay, there is still this fabric. And here's the Earth, and the more massive the Earth is, the more it stretches the fabric around it. So here's a little object, a satellite or a moon or whatnot, and it's sitting there and it interacts with the fabric. And it feels that the fabric over on this side is stretched more tightly than the fabric over on this side. And that fact alone, the fact that the fabric is unevenly stretched, causes it to get pulled in the direction where it's more tightly stretched. That is the reason why gravity works. That is also the reason why electric attraction works. So if instead of the Earth, we have a large positively charged object, and instead of the moon or the satellite, we have a small negatively charged object, it is exactly the same thing. This fabric, okay, is what causes it to be attracted. So when we talk about electric fields and magnetic fields, that's not just a mathematical abstraction that helps us to do the calculations more easily. It is a very real entity, okay? So back to the question of why does this electric charge, why does he feel a force? It's because the fabric of the universe has been stretched, and the thing that causes it to stretch is the changing magnetic field. It has to be changing. A static magnetic field doesn't do it, but a changing magnetic field creates an electric field. Okay, so as long as we keep flipping our battery here, this poor electric charge is going to feel a force going up for a while, and then down for a while, and then up for a while, and then down for a while, because the electric field around him is being stretched one way and then stretched the other way and stretched the other way. Now, here is where it gets really fun. What if that electric charge wasn't there? Okay. So, okay, let's try again. Okay, here we go. All right, so I've got my battery flipping back and forth. So the electric field is changing direction, but there's no charge there to feel the field, okay? So, you know, this is kind of like the question, what happens if a tree falls in the forest and nobody's there to hear it? Okay, kind of the same type of a question here. So even though there is not a charge physically present at that spot, the electric field is changing. And that changing electric field is going to have the same effect that a moving charge would have. Remember how a moving charge creates the magnetic field? You don't have to actually have a charge. All you need to have is the electric field. Okay, so when I have an electric field that's going up like that or down like that, even if there's not a charge there, guess what happens? This, okay? It creates a magnetic field. So you don't need to have a charge. Just the electric field going up creates a magnetic field. Electric field going down creates a magnetic field going the other way, okay? And so what we've got here is the electromagnetic fields have moved, okay? Now, what's going to happen here? So now I've got a region where I've got a magnetic field that's changing. Anybody want to guess what's going to happen around it? Here, I'll go ahead and tell you. That's going to create yet another electric field. And as long as everything keeps flipping here, that electric field there is going to appear. And this electric field that you see right here is due to the changing magnetic field that you see right there. Now, I'm sure you guys can guess where this is going. Okay, so that new electric field there, so there we go, sorry. Okay, so that electric field is going to create a magnetic field, and then that is going to create yet another electromagnetic pulse, and then that one's going to create, oops, okay, that creates yet another one. So you can see how this goes, and that creates yet another one, okay? So what we've got here is we've got an electromagnetic field that is radiating outward, sort of like a wave, you say. I'm glad you pointed that out. Not just sort of like a wave, exactly like a wave. What we've got right here, oops, sorry. Okay, let me go back here. Hang on a second, getting ahead of myself here. Okay. So what we've got right here is an electromagnetic wave. So you guys have heard the term electromagnetic wave. You've heard that a lot. Well, this is it. This is exactly what it is. An electric field, a changing electric field creates a changing magnetic field. A changing magnetic field creates a changing electric field. Okay, so Yazin is asking why are the number of lines getting smaller? Okay, well, because as it radiates outward, the energy is getting spread out over a bigger area. And so the amplitude of the wave is going to be going down. I mean, think of it like this way. Let's say you've got a lake, perfectly still water, no wind blowing. Drop a rock in the middle of the lake. The wave around the rock is going to be really big. But as that wave spreads out, the amplitude is going to get less and less and less and less. Okay, you got the same amount of energy, but it's spread out over a bigger area. Okay, so that's the reason when I made this drawing here, I did it this way, was to try and illustrate the fact that the strength of the wave gets a little weaker the further out that it goes. Okay, now I've shown it as it's going only in one direction, but in fact, it's going out in all directions. So you can see here that this wire right here, okay, the thing that started it all, that wire is the antenna. Okay, and so the electromagnetic radiation is going to go out in all directions around it horizontally. Now you might say, what about vertically? It gets really interesting when you go vertically. This particular antenna is going to radiate very well in the horizontal direction, and the further you get, the more vertical the waves are. But if you were standing directly above this antenna, you wouldn't get a good strong signal at all. In fact, not too long ago, I was talking to a guy who said that he was getting bad cell phone reception and he couldn't understand it. And what he said to me was, I'm standing directly underneath the antenna. I mean, there's an antenna right on top of the building here. I'm standing right underneath it. Why am I getting such bad reception? Well, because of the nature of how electromagnetic radiation works. If you got an antenna right here, it broadcasts very well in the horizontal direction. And the further out it goes, the taller it is. But if you were standing directly underneath the antenna, it doesn't radiate in that direction. Okay. All right, so what you've just seen here is electromagnetic radiation. Now, let's suppose that we want to pick on somebody. Who should we pick on here? Well, Milo is usually my favorite person to pick on. So Milo, I'm going to pick on you. So let's suppose that we want to really piss Milo off. We want to annoy him. So Milo, tell me, what's your favorite radio station? Okay, 101 or 105.1. All right, so Milo really likes listening to 105.1 on, it's on the FM dial. So if any of you would like to upset Milo, here's what you can do. If you go to Milo's neighbor, or somewhere in the neighborhood where Milo lives, if you take a wire and you string this wire up like this, and you take a battery and you flip the battery back and forth, if you were to do that at 101, or I'm sorry, 105, if you were to flip that battery back and forth 105.1 million times per second, so megahertz in other words, 105.1 megahertz. So if that's the frequency that you flip this battery back and forth, you will make Milo very unhappy. And so Milo, why do you suppose it is that you would be unhappy if somebody were to do that? You can turn on your mic, you don't have to type it. Interference with the radio station, that's exactly right. Because if you do this, if you do what I described here, okay, so let's see, we'll come back here. Okay, so we're gonna flip this battery back and forth 105.1 million times per second. We will have generated a radio wave. And that radio wave has exactly the same frequency as Milo's favorite radio station. And so it'll mess up the signal so he won't be able to hear his favorite radio station. So radio waves are electromagnetic waves, okay? And it's not just radio. Lots of other things are also electromagnetic waves. Let's see, okay. So in your book, in chapter 26, yes, light, you are exactly right, yes. So in chapter 26, there's this, little table, little drawing right here. This is a very, very, very important drawing. I want you guys to make note of this drawing. When I give the test that I'm going to give next week, if I do it, if we were back at Ames, if I was giving the test on paper, this chart that you see right here would be on the reference sheet that I would give you along with the test, because you are going to need to use this chart in order to answer several of the questions that are going to be on the test. So next week when we take the test, I won't have a reference sheet to give you, but I will tell you ahead of time, make sure that you have a copy of this chart right in front of you when you're taking the test, because you are going to be using this in order to answer test questions. Okay, so one of the questions that I might put on the test, wink, wink, nudge, nudge, would be name the different types of electromagnetic radiation. Okay, well, if you got this chart in front of you, you can just read it right off the chart. So you can see radio waves, we've already talked about those. Radio waves are an excellent example of electromagnetic radiation. So are microwaves. So when you guys take a burrito out of the freezer and you stick it in the microwave to heat it up, those microwaves that are heating up that burrito, they are the exact same thing as radio waves are. They are the exact same things as light waves are, and X-rays and ultraviolet rays and all that good stuff. Fundamentally, they're the same. The only difference is the frequency, okay? So one of the questions that I might ask on the test next week would be, what is the frequency of your microwave oven? And so what you would do is you'd look on the chart, you'd find microwaves, and you'd look over here and you'd say, well, it's pretty close to 10 to the 10th hertz. Maybe a little bit less. You notice as you go lower, the numbers get bigger, right? So it's somewhere between 10 to the 8th and 10 to the 10th, or you might say it's somewhere around 10 to the 10th. So, you just read it off the chart. So Milo is asking, is the chart in the book? Yeah, I'm very definitely. Let me see what page it's on. If you guys have your books with you, go ahead and get out your books. It's on page 7:08. Okay. So everybody, in fact, that would be good for you guys to do right now. I'll wait for a minute. Well, you guys get out your books, turn to page 708, and you'll see this chart. And what I'd recommend is get a bookmark and stick it in here, because when we take the test next week, you will absolutely positively need to use this chart, not just for one question, but several of the questions. Okay, and Milo is suggesting that if you need to get an online copy, you get that link right here. So if you guys would like to get an online copy of the book, copy and paste this URL that Milo just posted in the chat section there. And by the way, thank you, Milo, for doing that. Yeah. Okay, so let's go on with a couple more questions like the ones that you might see next week. You know how I like to start off with the easy questions and then they get tougher as they go on? All right, so one question that I might ask would be, what has a longer wavelength? X-rays or microwaves? Okay, so what you would need to do is you need to come down here and you need to look and say, okay, here's X-rays, and over here is the frequency, but I didn't ask about the frequency, I asked about the wavelength. So then, okay, no problem. So instead of looking to the left here, you look to the right. And you'll see that X-rays are right around 10 to the -9th meters, which hopefully you guys recognize is a nanometer. Okay, so the wavelength of an X-ray is about 1 nanometer. Now let's come up here and let's look at microwaves. The wavelength of a microwave is somewhere in between 1 centimeter and 1 meter. Okay, somewhere in that range there. Okay, so clearly a microwave has a longer wavelength. The X-ray has a shorter wavelength. So that's the type of question that I might ask at the beginning of next week's test. Now, as the test goes on, the questions get harder, but I do like to start off with easy questions at the beginning. Okay, now you might wonder why they have these funny pictures over here on the right side. And that's just basically to give you some sort of a sense of scale. So if you look at the wavelengths here, you know, like 100 meters or 10 meters, you know, that's about the size of a building. So a radio wave has a wavelength that's approximately the size of a building, okay, depending on what radio station. Okay, microwaves have a wavelength that's approximately the size of a baseball, okay. Infrared, you're getting down somewhere in between an insect and an individual cell. Light rays, visible light, okay. This part of the spectrum that you see right here, you'll notice is just a tiny part of the spectrum. That's the only part that our eye can see. So if your eye can see it, we call it light. If your eye cannot see it, we don't call it light, but they're all the same. It's all electromagnetic radiation. Okay, so visible light has a wavelength that's approximately on the same size as a virus, you know, kind of like the coronavirus. Okay, X-rays and gamma rays, we're now we're down where their wavelength is, you know, on the scale of like a molecule or so. Okay. All right, so hopefully you guys will find that this chart is very, very helpful in the tests we're going to take next week. Let's see. Okay, well, let's go on. Okay, now what I've done here is I've zoomed in a little bit just to make it a little bit easier to see as I ask a couple questions here. Okay, so all of these that you see here, they are all examples of electromagnetic radiation. They are all fundamentally the same. The only difference is the wavelength or the frequency, you know, same thing, same difference. Okay, now, if I were to ask you how fast they travel, you know, if I were to ask you like on next week's test, I say, what travels faster, a radio wave or a microwave, okay, or something else? You should recognize that the thing that determines the speed of a wave is properties of the medium. That's another Hendricks catchphrase that I've said many, many, many times, right? What is it that determines the speed of a wave? Properties of the medium. Well, if the medium for all of these guys is the same, the medium is the electromagnetic fabric of the universe, that means the speed of these guys is going to be the same. So the speed of a wave, of a radio wave, is the speed of light. The speed of an X-ray is the speed of light. Okay, so hopefully you guys will all understand that. Okay, they all travel at the speed of light. All right, so one of the questions that I might ask on the next test would be, you know, if I've got a infrared light wave that has a frequency of 110 hertz, I might ask you to calculate the wavelength. Now, if you've got this chart, you could just look it up. But if you didn't have the chart, you could use everybody's favorite equation, lambda equals V over F. So if V in this case, for all of these guys, V is going to be actually C, is going to be the speed of light. So you can use that to calculate it. Or in this case, you just look it up. Okay, now, this chart is typically divided up into 3 regions, okay? The region in the middle here is visible electromagnetic radiation, and it is just a tiny fraction of the overall electromagnetic spectrum. Any part of the electromagnetic spectrum where the frequency is higher than visible light, we call that ionizing electromagnetic radiation. And anything where it's lower, we call that non-ionizing electromagnetic radiation. So those of you that are in chemistry, think back, what does ionizing mean? If something is ionized, if Coach Miller is talking to you about a chemistry problem and he said, this thing got ionized, what does that mean? It has a charge. And why does it have a charge? Because somebody has either stolen an electron away and leaving it with a positive charge, or maybe something has added an extra electron in, so it has a negative charge. Okay, so in this case, when something gets ionized because it got hit by high frequency electromagnetic radiation, it's always going to be the case where the electron gets pulled away. So if an X-ray comes in and hits a molecule, that X-ray is going to get absorbed by an electron, and that electron is going to get pulled away. So it's always going to be left with a positive charge. Well, molecules having electrons get ripped away from them, that's a bad thing. Okay, that's how you get sunburned, and that's how you get cellular damage. If you go in to have an X-ray, you know, when you go to the dentist, they always put that heavy lead cloth or that lead apron on top of you. And then the person who's taking the X-ray, they always go and stand behind the wall, because X-rays are bad, because X-rays are ionizing radiation, okay? And so that can really hurt you. So anything in this part of the electromagnetic spectrum, you want to avoid that, because it will damage your body. The stuff down here on this side of the visible light range, that is non-ionizing radiation, so it's going to be safe. It's not going to hurt you. Okay. Now, I'm hoping that one of you is going to recognize a problem. Let's see, we're running a little short on time. So rather than me waiting for one of you to recognize it, I'm going to go ahead and point it out here. Okay. What about microwaves? Now, I just got through telling you that microwaves are down here in the safe part of the electromagnetic spectrum, the non-ionizing part, okay? But you guys hopefully know that if you put a cat in a microwave, which I do not recommend, in fact, please do not. Why? Because it'll kill the cat, right? Microwaves are dangerous. And yet, I told you that they're down here in the safe part of the spectrum. Okay, so Yasin is saying myth. It's not a myth. There is something really interesting about microwaves that makes them dangerous, and it's not because they are ionizing. Okay, so Hiram is saying any else's parents tell them not to stare at a microwave. Yeah, I hope they would. Now, actually, the microwave oven has a special screen on front of it, so hopefully it's preventing the microwave radiation from getting out. But if that screen was scratched, then yeah, that would be bad. Microwave radiation could get out, and so your parents are right by telling you not to stare at the microwave. Okay. Ah, Bridget. Yes, Bridget is saying it contains water. Izzy is saying it's harmonic frequency. You guys got it exactly right. Okay, that is exactly what's happening. The reason microwaves are bad is not because the frequency is in the ionizing range. It all has to do with resonance. Remember the Tacoma Narrows Bridge? Remember how we had the bridge where the wind just happened to pulse, because of the shape of the mountains and the channel there. They built up little eddies, and so the wind would pulse. So the wind would hit it, and then the wind would hit it again, and the wind would hit it again, but it wasn't hitting it very hard. The strength of the wind was not the problem. The problem was, you know how every object has a natural frequency. If I hit something, it likes to vibrate at a certain frequency. Every object has a natural frequency that it just naturally likes to vibrate at. So do molecules, okay? The water molecule has 3 different modes where it can vibrate, okay? And so it is a miniature version of the Tacoma Narrows Bridge. And so microwaves, by sheer coincidence, just happen to be exactly the same frequency as the fundamental frequency of the water molecule. So here's a water molecule, and the microwave hits it, and then it hits it again, and it hits again, and it resonates exactly the way that the Tacoma Narrows Bridge resonated. And so that water molecule gets really, really hot. And that's how your microwave works. So that's why whenever you're using a microwave, you want to make sure to use a good quality a ceramic plate that has no embedded water molecules in it. If you take a plastic plate that is not designed for microwave use, so then you take your burrito, you put it on this plastic plate, you put it in the microwave. The plastic plate will get hot because it has embedded water molecules in it. Whereas the high quality China plate will not, because it does not have there. Okay, so Hiram is asking why you shouldn't put metal in the microwave. Okay, so the reason for that one is different. The metal acts like a lens. And it takes the microwaves, if the metal was perfectly flat, maybe you could argue it might be safe, but it's never going to be perfectly flat. There's always going to be a little bit of curvature. And so it takes the microwaves and it acts like a lens, and it focuses the microwaves in on one little spot. And so then all that energy gets focused into a tiny spot, and that creates problems. So that's the reason why you shouldn't do that. Okay, so this is the kind of stuff I might put on the test. And pretty much we are done. It's been almost exactly an hour, so it's perfect timing. I like these classes to last for about an hour. Okay, so when you read the book tonight prior to doing the homework, because I know you always read the book before you're doing the homework, right? Okay, the first part of the chapter, you can go ahead and skip that. It contains information which is very interesting, and I encourage you to read it, but I don't think it's necessary. Some of the stuff that's in there we've already talked about, like how does a cathode ray TV tube work? We've already talked about that. And then the other stuff is stuff that I'm not going to put on the test. So don't worry about pages 697 through 704. Start reading on page 705, where it talks about electromagnetic fields in space, and it talks about basically the things that we've already talked about. Okay. All right. So your homework is tonight. Your homework for tonight is here. Chapter 26. You only need to do problems 15 through 21. Okay. And then on Friday, what we'll do is we'll talk about the homework. And I will also talk about a few other things on Friday, some of which are in the book and some of which is not. And it is stuff that I do want you to know. And it is stuff that I might put on the test next week. So make sure that you show up on Friday or watch the recorded video. On Friday, I'm not going to give you a homework assignment, but the quiz will be a little bit harder than a normal quiz is. You will need to watch and pay attention and make notes. And then on Monday of next week, I will pass out the practice test. On Wednesday of next week, we'll spend the whole day just going over the practice test. Oh, and by the way, on Monday, we'll do a little bit more review as well. So, I mean, we will be talking about some things during the Monday class that will be worth your while to attend. Okay. But then I'll pass out the practice test. On Wednesday, we'll spend the whole day going over the practice test. And then on Friday is when we will take the real test. And I'm going to do this next week's test the same way that I did the previous test. Everybody has to take it at the same time. This is a security requirement because I need to make it a lot harder for you guys to cheat. I realize if you really want to cheat, you will find ways to cheat, okay? But I need to at least make it hard, okay? And so this is a firm requirement. Everybody must take the test at the same time. So if you have a brother or sister who needs the computer, and the two of you are competing for only the one computer, tell them now. And if you have parents who are working from home and they need the computer to work from home, tell them now so that everybody can plan ahead. So that on Friday of the next week, between 1 and 2:30, you have exclusive use of the computer. Okay, well, that's it. I see it's 1:56, so perfect timing. Anybody want to ask a question before I turn off the recording? Okay, so Cohen's saying that if magnetic fields stretch the electromagnetic field and light propagates along the electromagnetic fabric, then could magnets bend light or other electromagnetic waves? If it's a stationary magnet, it doesn't affect anything. But if it's a magnet where you're increasing it and decreasing it, if it's an alternating magnet, yes, definitely. But remember, a stationary magnet, a magnetic field that is not changing, it has no effect on the electromagnetic field. Okay, Milo wants to know, will the test be open book and open internet like it was last time? The answer is yes, it will. Okay, any other questions? Why does broccoli spark in the microwave? I didn't know that it did. Well, that's interesting. I don't know. So if anybody, does anybody know? I didn't even know that it did spark in the microwave. Tell you what I'm going to do, Maddie. This afternoon, I'm going to go get some broccoli and put it in the microwave, and I'm going to see if that's true. I had never heard that before. Ah, okay. Milo is saying you can make a plasma by putting a grape in the microwave. Yes. Oh, you can do some fun things. Yes, you guys have all seen that. I've seen those videos on YouTube where they take a grape and they do that. That's really cool. Okay, so I'm thinking we're done here. Okay, will the curve be higher on this test as it's harder to understand than online? Okay, so when I grade tests, I always do it two ways. One is straight percentage and the other is curve, and it's not a fixed curve. I adjust the curve depending on how people did. And if everybody's scores are a little bit lower for whatever reason, I adjust the curve accordingly. So yeah, Yasin, don't worry about that. And by the way, Yasin, do you find that it's harder to understand things online? Because I've had a couple students actually tell me the opposite. I've had a couple students tell me that these videos that I'm doing where I spend, I don't know if you guys realize this, but I spend like 4 hours preparing for a 1-hour lecture because I go out and I find the right picture and I put in the picture, and I spend a lot of time with these pictures. And I've had a few students tell me that because of the high quality of the pictures, they've found that it's actually easier to understand things this new way than the old way. But Yasin is saying, oh, it's harder because you used to go in during lunch in order to ask questions. Yeah, I agree with that. Okay, so let's see. Somebody had a question that has scrolled off the screen here. Okay, so Anna wants to know, will the grades change from A to F to pass or fail? They're going to stay A through F. I'm not doing pass or fail in this class. Absolutely not. Let's see. Anybody else? Okay, so Dean is saying. Now this is Dean saying. I don't vouch for the accuracy of this or not. But Dean is saying that broccoli sparks because there's lots of iron and other metal nutrients in the broccoli, so it sparks for the same reason the metal does. That's an interesting conjecture. Oh, he just Googled it. Oh, well, that's interesting. I'm going to have to Google that one myself. That's interesting. Okay, so Before I stop the recording, okay, any serious questions? Going once. Going twice. Oh, yeah, we did the secret word. We don't need to do that already. Okay, going once, going twice. Sold. Okay, I will stop.